This course does not use calculus, but it does use a lot of algebra, so it will be useful to review some of the techniques and patterns of algebra. That's what this video is for. In its simplest form, algebra is about number puzzles. If you had to explain it to a child, you might say something like this. Here is a mystery box. It contains a number. If I add 3 to this number, I get 8. What number is inside the mystery box? And she would answer 5. Now, in algebra, rather than talking about mystery boxes, we use letters to stand for unknown values, but the purpose is still the same, finding those unknown values. We can systematize the way that we solve equations with one unknown. The idea is to isolate the unknown by reversing all the operations done on it. We always go in reverse PEMDAS order. First, if any number is added to the unknown outside of any parentheses, we subtract it from both sides. Likewise, if anything is subtracted outside the parentheses, we add it. Next, if the unknown is divided by anything, we multiply both sides by that number. And if it is multiplied by anything, we divide both sides. Then, if the number is raised to a power, we take that root on both sides. If a root is taken of that number, we raise it to that exponent on both sides. Then, we repeat the steps all over again until the unknown is isolated. Here we end up with x equals 509. That's the number inside the magic box. This technique for solving unknowns applies to many algebraic equations with a single variable, like this one, so we'll use it a lot. Here is another type of algebraic equation. You'll notice it has two variables. The purpose of this equation is different. It doesn't provide a puzzle with two unknowns because two unknowns require two equations to be solved. Instead, it provides a relationship between the two variables. If you provide a value for x, you can use the equation to calculate a value for y. This type of equation is called a linear equation, and we can show several examples. They are called linear because when you graph them on a Cartesian plane, you get a straight line that extends infinitely far in both directions. In physics, many equations of motion are linear. All the equations you see have something significant in common. The x does not have an exponent. Sometimes it is multiplied by something, and sometimes it is added to something, but it never has an exponent. This is characteristic of linear equations. Linear equations have several interesting qualities, but the most relevant one for us is this. Pick any value for x and solve for y. Here we'll plug in 1 for x. We find that y equals -1. Now, let's increase x by 1. When we recalculate, we see y has increased by 2. Increase x by 1 again, and y increases by 2 again. In fact, every time you increase x by 1, y increases by 2. This behavior is caused because of the number being multiplied by the x. In a linear equation, a coefficient of 2 means that every time x changes by 1, y changes by 2. A coefficient of -5 means that every time x increases by 1, y decreases by 5. A coefficient of 0.3 means that every time x increases by 1, y increases by 0.3, and so forth. A special case occurs if you don't see a coefficient. In algebra, if the coefficient is 1, we don't write it, but the same logic holds. A coefficient of 1 means that if x increases by 1, y also increases by 1. There's another class of equations we will see, called quadratic equations. Unlike linear equations, where we didn't see an exponent, here one of the x terms is squared. It has an exponent of 2. All quadratic equations follow the same basic pattern. There is always an x squared, and it might be multiplied by a coefficient. We symbolize that coefficient as a. There is usually an x term, and it too might be multiplied by a coefficient. We would call that b. And finally, there is usually an additional number added. We call that c. Quadratic equations always have the highest power being 2. They can never have a power of 3 or anything higher than 2. If we were to plot these equations on the Cartesian plane, we would get these shapes. This type of shape is called a parabola. Parabolas and the quadratic equations that form them are supremely important in physics. In fact, they are the backbone of kinematics. You'll notice that parabolas are symmetric shapes. Most of the ones we see here cross the x-axis twice. Those locations where it crosses the x-axis are known as the roots or the zeros of the parabola. It's pretty common to need to find the zeros, and we have this equation to help us. It's called the quadratic formula. Finding the zeros of a quadratic equation is easy using the quadratic formula. We just need to substitute all of the coefficients into the formula. We simplify the term under the square root first, and then take the square root. Now, you probably noticed that plus minus sign in the formula. That simply means that we need to solve the formula twice. One version by adding the root, and one version by subtracting the root. And then a little simplification will lead to the points at which the parabola crosses the x-axis. For this original equation, the parabola crosses the axis at x equals 0.5 and x equals 3. Now, you might see cases where the number under the square root sign turns out to be negative. You might have learned in your math classes that taking the square root of a negative produces something called an imaginary number, a wondrous, intriguing concept with many theoretical and practical applications. But for this level of physics, we will not be needing imaginary numbers. In these cases, we will just say there are no real solutions. This is a summary of the techniques of algebra that you'll need for this course. The next video will introduce some of the basic trigonometry that you need as well.